But still I'm humbled. The previous speakers have shown that they have done game-changing things. We are at the very early stages of doing so. Obviously we have the hope and also the vision to do that. It is about the fact that we unite the human brain with the machine brain, which will be the end stage, and I'm pretty sure that will happen. So this opens up a lot more discussion on what will happen in the next 20 years than what we did. I have the unique opportunity, or we have the unique opportunity here in Munich to gather people in one spot who at least have the capability of being a leading hub for that type of thing. I will be introducing it as the person who is responsible for organizing this and also taking the responsibility of everything that happens. Because for the time being, it's a surgical issue. We're doing invasive implantation of so-called brain-computer interfaces. And my short talk in the beginning, I will give you just an overview on what that means, and probably you understand why we are the first ones. How can I advance my slides? Do I have anything? So in December 2025, the president of the Technical University of Munich announced that our project was one of the top 5 for the Technical University. It has caused a lot of media attention, which was good for us because it caused then the attention of politicians, of people who want to collaborate with us on the academic level and other. So the question is, why were we the first ones to implant this type of thing? And I will introduce someone who will be later on the stage, who is basically the main act. That's Mehringer. He is actually, I tell you this story backward, the second implantation, as it was the first one in tetraplegic in Europe. And we don't call it patients. He's a participant. He's one of the key players in everything. And probably, I always say, his name will be remembered in 20, 30 years when mine is still forgotten. Actually, that was the second time that we implanted chronically, and already 4 years before, this lady was the first time in the world where we implanted something similar, but on the other side of the brain, because one side where you speak with was destroyed. This is, or has been, and still is, the first and only worldwide. That was 4 years ago. She's a bit in the shadow because she's shyer than Michi, but nevertheless, she has the same open personality. On one hand, they are very, very selfless because they know exactly that the profit they have from this type of procedure is much less for themselves than for society. On the other hand, they also know what they're doing because they have a purpose in life. So they are connected. There are around 50 people in the world who have this type of implant, and they're all alike. They all have this same personality traits. These are the two. These are medical data which are not probably so important or relevant to you. I just tell you that these people have something implanted which is a highly experimental and very archaic implant. This is not the thing that will be implanted in the future. Markus Söder just related to that. This is where the development started, but this is a 20-year-old implant that has been primarily implanted. It's called the Utah array in primates 20 years ago, and as I said, Mickey was the 50th patient in the world which has received this implant. Before we did that, we trained on having people who were having brain surgery for tumors in an awake setting. That means they are awake while I do the tumors. And implanted these type of things, 13 in total, which is the world's largest series to date of acute implantations. That gave us several hints which are very specific and which probably are not interesting to you, but The question was, how much trauma do we do? How do we root the virus? And so on, and so on, and so on. With that experience, because you only have one single shot, which was very, very decisive for us. Before even that, so what we did was to implant these type of things, we transferred what we did routinely in oncological surgery, that is in tumor surgery, onto BCI implantations. We have an 18-year history of precise planning and preparation for tumor surgeries with a method that is called navigated transcranial magnetic stimulation. Basically, there's a map created, very, very precise on a sub-millimeter level where the functions in your brain are. And that is the prerequisite of doing any implantation at all. So 10 years or even 15 years ago, we had this established workflow, which is very, very important, and not everybody has it. And this is one of the features where we're the only ones in Europe that have done this type of thing. Without that, and taking everybody who works in your OR, which are nowadays 20, 25 people per OR, you can't do that. So we were lucky to have that. And among other prerequisites, when I had the idea about 12 years ago, you need to team up with someone who is a basic scientist and very, very knowledgeable in this type of thing. This is my partner, Simon Jakob, who will be speaking right after me, who does the neurophysiology and who is a key person in this thing. And you need to be, first of all, willing to work on eye level, and be, as a basic scientist who has done this in animals, to transfer your knowledge into human beings, which is not as easy as you think. Now, for those of you who are a little bit faint of heart, but because journalists usually ask how the procedure works, I will show you some pictures. So you will see an open brain. If you don't like to see it, just look at the floor. So this is a publication that Arthur Wagner just has out in a very prolific term, which shows what we have done. It starts with planning. These are the two patients. The first patient on the left was the lady, and the other one on the right, you will see right after, live on stage, is Mickey. And these are the points in the brain where we implanted this. Before we had the opportunity to do this, we had to do a lot of planning. This is a CAD reconstruction of his actual brain and skull. And you need to train the surgery there because these are individualized implants, and we need to know exactly where we anchor the socket, where we route the wires, how long the wires can be, etc., etc. So that's how actually your brain looks like. During the actual implantation, you see this is a navigation device. This navigation device tells us exactly where we need to implant this type of arrays. That's how the arrays look like. You see that one is in place and the others are still upside down. These are 64 spikes of 1 millimeter length, which are shot into the brain by a certain instrument. I'll spare you this because I don't think that is something you want to see. If everything goes well, it doesn't mean that you have done your job, because it takes about 4 to 6 weeks until we know that the signals are stable and how many of the 254 spikes will send signals where we can record. So Simon is usually very anxious during this time and very pessimistic. I'm not. I'm very optimistic, and this was a very lucky shot. So we have 254 out of 254 going very, very stable. Now, what comes next? We have overcome these problems here. We have very good imaging. And we can do the surgery exactly and position it exactly. And now the question is, why didn't it fly before? Because now we have the accessibility of large data, and decoding could be possible, which hasn't been possible before. This is why everybody invests now, why everybody wants to be part of the game. And before that, that was impossible. That creates other problems. One is, as you see, Mickey needs a physical contact to his computer. Obviously, that's not feasible for patients. It needs to be underneath the skin. It needs to be done at home. Otherwise, you can't use it actually in clinical routine. So what we're doing with another round of support, several millions from the BMBF, we're trying to achieve this goal by helping other companies, especially companies which are here in Munich, to develop these type of implants, which takes a surgical or a surgeon who is willing to transform his OR into a human laboratory, which I am willing to do. And then we will probably create, in the end, chips which no longer not even need physical contact, but also are capable of reducing the mass of data which needs to go outside. So to cut this short, we have now a Munich Research Alliance created and founded, in the inner circle of which are the ones you will be here today, besides me, Simon Jakob, Lorenzo Masia, and it will be Georg Starke talking for Jenka. Then we have the outer core, and you see that many, many companies, among which is BlackRock, Google, etc., and especially Brainlab. You will hear the CEO talk about that, a local world leader without whom we couldn't have achieved this talk. And they're all part of this research alliance. We have an ambitious goal that in the next 5 years we establish not only the #1 position in Europe, but at least among the first 3 globally. And then I will retire, and my successor has then, in the next 20 years, the task to transform that into clinical routine. Just one thing. This is human enhancement. This is a very, very good article from Time. And it will show you, if you read it, your future. I'm convinced of that. Nobody, not China, not the capitalist mark, invests so much money just because of the patients. If you think so, you're wrong. It's about human enhancement, you, to speak better, to run better, do whatever better. It will come. And I have, according to me, because I'm a gate opener to that as a doctor, the responsibility to say, okay, I'm a gate opener, so I try to be open, to be transparent, and within every ethical limit. You should ask yourself the same question if you want to think about it now and be part of it, or just tagging along. So with that, I end, and I have Simon Jakob talk about BCIs more in general, what it means and what it takes. We will have a discussion round in the end, so all the questions that you have can be asked later on. Thank you very much.
Good morning. Thank you very much for having us. It's a great pleasure. My name is Simon Jacob. I head the chair for Translational Neurotechnology at the University Hospital of TUM. My role is that of a basic scientist, but my training is in fact medicine, and this is what makes things possible. If you bring worlds together, I tend to fuse different worlds in my little brain. That helps a lot. It's great to be in Munich. Great to be in this environment. I think we're all in the same spirit. You have to bring together ideas and put them as close as possible as you can, and then boom, magic will happen. And as Bernhard has been introducing the field, this is something that does not work by single people. This is something that needs large teams that work together over long, long time periods. And we stand here as physicians, basic scientists, engineers, ethicists, But nothing here works without the BCI pioneers. And if you gracefully give me a few minutes to introduce the science, what I will then do afterwards is bring Michael on stage, and you will get to know the first European intracortical microelectrode implant for spinal cord injury. And Michael and our team, we will start to showcase and talk a little bit about how it is to be a pioneer. I don't know what it feels like to have electrodes in my brain. Michael is one of 100 or a bit less participants in the world who have this experience. So, what I want to do in the next few slides is introduce to you where we stand and where we're going in the field of invasive, implantable brain-computer interfaces. Bernhard has already introduced the technology. The idea of a BCI is you take signals as close as possible, ideally from the brain, because that's where the neurons generate the signals that are us, and you transfer those to computer devices, to robotic devices. We will have Lorenzo talk about the fantastic exoskeleton engineering solutions we are building together. And then you have to digest all of this data that's coming out of brains. We have hundreds of channels at the moment. The future will be tens of thousands of channels. So, again, in the spirit of here, DLD and BAIOSPHERE, nothing here works without AI. You cannot look at single neurons anymore and understand what they're doing. And to give you a flavor, every single patient who is implanted with one of these brain-computer interfaces, Michael produces every single session that he comes to us about 100 gigabytes of brain data. That means per year, he averages about 15 terabytes. Your hard drives on your standard PCs might have a terabyte, a little more, so he's basically producing 15 hard drives a year, or one hard drive full of sensitive brain data every month. This means that just in TUM alone, just our center here is producing per year, or the next few years, easily petabytes of data. This is not just something Facebook clicks or so, or Meta clicks. This is sensitive brain data. So we have all of the implications that come with responsible medicine, responsible engineering, AI, and responsible research and innovation. That's why we're very proud to have our colleagues of ethics on board here as well. This is all interdisciplinary work. Where we stand right now is we're reading from the brain. So the idea is you use AI to decode what is going on in your brain. You have to make sense of it in some way to restore lost brain functions. Michael is a fantastic example of what can be achieved, and not just us now in Europe. We are standing on the shoulders of giants as well in the US, so we've had a few years of experience already in reconstructing movements. So I would say mobility, regaining independence, that's the primary, it was the earliest goal in these implantable brain-computer interfaces. But there's another new, something new on the horizon that I want to take a few minutes before we go to Michael to talk about, which is restoring communication. What I'm doing right now is marvelous. I'm creating sound pressure waves. I'm bombarding you with sound pressure waves that in your minds are instilling thoughts. This is the gift of the gab. Right? So this is talking to you, I'm communicating my thoughts and instilling in you your thoughts. And this is something that is lost in many participants and patients who have various types of brain disorders. Not being able to communicate is one of the most drastic things that can happen to you as a human being. And the primary example of this is going to be amyotrophic lateral sclerosis, which is a neurodegenerative disorder you might have heard of that robs people of the ability to move. At the end, it robs the ability to breathe. They die, they suffocate, and on the way to this state, they very often lose the ability to communicate because they lose the ability to speak. The speech motor tract fails. They cannot output the signals that they intend to communicate. And this is where intracortical brain-computer interfaces have been a complete game changer. I've been in this field for about 10 years. 10 years ago, I wouldn't have thought that we would be here right now. So what I can now show you is a video from our colleagues in California. This is from Stanford and UC Davis. And what they've done is they've implanted exactly the technology that Bernhard was talking about and that we also use in a patient with amyotrophic lateral sclerosis. This patient normally is mute. He produces no speech output whatsoever. Completely nothing. No ability to communicate like I'm doing right now. And what our colleagues are doing, they are reconstructing from the cellular resolution data of his brain the intended words like a speech output. So I will play the video. Technical staff, can you please crank up the audio? This is very important. So you'll see the patient, he's in front of a computer screen, and you will be able to read off the sentence that he's intending to produce. And what you will hear is a computer-generated output of his speech. This is not amplification of his own natural speech. This is computer-generated. And I hope you will see the correspondence of reading the sentence and hearing what the computer produces for this ALS patient. Again, fantastic work, UC Davis.
You need help. Do you
Question, intonation up.
need help? You are having you are having
You can see this is effortful, right? This is the patient is trying hard. But the output normally is 0. This is a heaven sent for these types of patients. This is completely generated from brain data. So luckily, ALS is not the dominant communication disorder. It's fate, terrible for the individual, terrible for the stakeholders, but luckily not the greatest burden on our medical society. The problem is this. This is what hundreds of people in Munich have, thousands across the Munich metropolitan area, hundreds of thousands of people in Germany, and worldwide. This is a brain lesioned by stroke. Stroke has destroyed, you don't have to be a medical professional, you can just use symmetry left and right. What you're seeing here is a 3D reconstruction of a brain of the worldwide first participant for language disorders. This is not a speech disorder. What this lady has, Maria, she has an inability to form words in her mind that allow her to communicate. She does not have an articulatory problem. Her problem is not cleanly outputting her speech. Her problem is finding a word that communicates her rich inner world. That's something that we medically call aphasia. This is the global burden on communication, because that type of stroke, it can be traumatic brain injury, it can be tumor resections, sequelae, it can be bleeding, hemorrhages, robbing you of the inability to form words and output language. That is the frontier in communication. The problem with that, we do not know what to decode. We don't know how the human brain produces language. So what we have been doing over the last few years, we've also been working very hard at basic science, using brain-computer interfaces to research breakthrough science with the same devices that Bernhard introduced. And I will now play the video of Maria communicating with Laura Schiffel. Laura's our clinical linguist, and Maria will be trying to find words for her condition. And you might now notice the big difference to the articulatory problems that ALS patients have. She does not have an articulatory problem. She's lost for words.
Kannst du noch mal erzählen, wie das mit der Erkrankung angefangen hat? Wie war das damals?
Ja, arbeiten und Heike und ich shoppen und dann umgefallen, alles weg, wo bin ich, und dann zeigen, sprechen schwierig und dann üben, einfach so. Ja.
So you can see the point. Everything that she said was crystal clear, even though you might not be a German native speaker. Her problem is that, what is it, what am I trying to say? And that's the most drastic medical problem in communication. So what do we do here? And this is a pioneering thing that Bernhard Meyer, Jens Gemt, and Arthur performed together with both of our teams in the planning. They implanted the very first intracortical microelectrode BCI for language disorders. This was in 2022. This is the pioneering early days of reconstructing language, not speech, from human brains. Now, this is where science comes in. We do not know what to reconstruct, and it's still the early days. But what we know is that with the cellular resolution data that we have an option in the future to reconstruct the words that she's lost. And the daring thing here was to see where in the brain will we put our electrodes. The left hemisphere was destroyed. You might know that the left hemisphere is typically the language-dominant hemisphere, even if you're left-handed. So the daring thing here was to implant in the right hemisphere. That's the one that is left, and is a bet, almost a leap of faith. Not exactly. There's some scientists that we could talk to see whether this might be the right approach. And what I can show you now is that the right hemisphere is heavily language competent. So in Maria, what we have found, no matter on which of these 256 microelectrodes we look at, we find a huge, beautiful, rich world of neural signals that capture the words that she's trying to formulate in her mind. Across all 4 arrays, no matter whether you're producing words, you're understanding words, or you're repeating them, the neural signals can be decoded. And this is the future for us, now with AI, to see whether we can turn these basic science signals into something that gives her back the word that she intends to produce. This is where we stand. So, writing the brain is the future. We've heard from Marco Söder about the biohybrid type of interfaces. There will be fusion of biology and engineering. That's more on the hardware, on the device manufacturing side. What these electrodes that we have right now already allow us to do is to pass currents, electrical currents, through the electrodes right into where the neurons normally generate electrical currents. Which means if you know which signals to stimulate, what you can do, you can reconstruct the naturally occurring signals that, for example, would allow you to see. If you're blind, there are options of stimulating the occipital cortex, the visual cortex of the back of your brain, to reconstruct crude percepts. This already works. This has been studied and already published in very reputable clinical journals. We're on the early days of having trials for restoring vision by passing current through precisely those electrodes that you now know very well. And we have touch. Touch is so important. As I'm standing here, my brain is bombarded with sensory signals coming through my feet. This is such an important signal for all body functions. And now, for patients with spinal cord injury, the future will not just be to reconstruct movement, but if the robot touches something, you can feed back the sense of touch via those electrodes. So you go full loop, motor and sensory back. This is something that is on the horizon here and also will be happening for us in Munich. So, where do we stand? I said 100 patients roughly implanted with some intracranial neurotech. How many of you know how many people have been to the moon? Have a guess. 70. Yeah, okay, good. 17, yes, it's 12. Right, so 70 is great, but I would like to have that comparison, but it's actually just 12, right? So, well, my point is 112, yeah, it's the same ballpark range, right? We're talking about pioneers worldwide who've received this technology. We only have 100 people. You're going to meet one of them right now, right? And we have a second one, Maria, that you saw on the video. But the problem is, of course, very obvious. I was talking about stroke, traumatic brain injury, bleed, neurodegeneration, you name it. We're on the order of hundreds of millions of people. And you will have the pleasure of listening to a few colleagues of mine over the course of the rest of this morning, but later this afternoon, where we have to get these ends to meet. We cannot implant everybody, right? So we will need scalable technology. So this is an engineering collaborative effort across all of the disciplines, and we have to bridge that gap. But the market is huge, the need is huge, and intracranial brain-computer interfaces, or neurotech in general, is there to stay. So, the FAZ featured us very recently. I think they put it quite right. This is a worldwide race. We don't just have TUM, LMU, Helmholtz, Max Planck or something, Bavaria. We have the whole world racing. We're fusing, merging these machines and computers. So we have to be the ones that make the right decisions. But what we want to do, we want to move forward in a responsible way, We want to link in ethics, medicine, AI, engineering. We want to bring all the stakeholders together. And we're very lucky, we're like with DLD support and everything here, we have the right community. So this is the time to strike the iron while it's hot. Thank you very much for listening. Now I'll have the immense pleasure of bringing on Michael. Thank you so much for now. Big round of applause. So, wir schalten jetzt mal auf Deutsch um. Das ist für uns beide ein bisschen einfacher, oder? Michi, machen wir so? Ja, gut, super. Ich halte einfach das Mikrofon hin und was ich vorschlagen würde, wir wissen schon, du warst ja schon in jeder deutschen Tageszeitung, du warst schon in jedem deutschen Magazin drin. Ich würde trotzdem mal gerne kurz von dir hören, wie bist du auf uns gekommen? Wie war das so mit der ganzen Forschung, die wir machen? Wie hast du denn uns gefunden überhaupt?
Also, erst einmal...
Sorry, is this on? Do I have to press mic? If in doubt, press mic.
Jetzt.
Jetzt geht's?
Jetzt, nee.
I'm quite sure it's not working. I can just switch. Wir warten mal kurz, sonst verstehen ich die Leute ganz hinten nicht, ne? Ist ja wichtig. Oder ich schalte einfach auf das. Let's take. They're also dead. Ah, no, hang on, this was working. So, jetzt aber. Okay, also, wie bist du auf uns aufmerksam geworden?
Das erste Mal, grüß Gott, ich bin aus der Michi. Wollte mich kurz vorstellen.
It's still not great audio-wise. I can take off mine if you want to and then switch it, but that might be not the right. Ja. So, warte mal. Ich nehme das mal ab und dann einfach hin und her.
Aufmerksam geworden bin ich durch meine Mama, die jeden Tag Zeitung liest. Und da war ein Artikel in der Zeitung mit KI, mit Hilfe von KI und Zukunft einen Roboter bedienen für Querschnittsgelähmte. Und dann hat Mama den abfotografiert und den Artikel mir geschickt zum Lesen, also quasi digital. Und ich habe mir gedacht, zu dem Moment, ja, querschnittsgelähmt bin ich ja, bin ja wahrscheinlich ziemlich genau gemeint damit. Und in diesem Zeitungsartikel war natürlich sehr interessant. Und dann stand eine E-Mail-Adresse drin von der Studie und da habe ich auch eine Nacht drüber geschlafen, weil das ja doch ein erster großer Schritt ist für mich. Und dann habe ich am nächsten Tag hingeschrieben und wurde vom Professor Simon Jakob ziemlich zügig auch zurückgerufen.
Kannst du uns noch mal kurz beschreiben, was dir zu Hause... Was fehlt dir zu Hause? Was ist das, was du am meisten bräuchtest?
Also in erster Linie Freiheit, also Selbstständigkeit, dass ich mein Umfeld, also meistens sind es meine Eltern, wieder, dass sie sich frei fühlen können und tun lassen, was sie können und wollen, ohne ein schlechtes Gewissen zu haben. Und geht es unserem Sohn zu Hause gut, wird er gut versorgt. Das wäre eines meiner größten Wünsche.
Das ist genau die Gelegenheit zu sagen, jeder, der mit Menschen mit solchen Erkrankungen arbeitet, der weiß genau, wie viel hinter den einzelnen Patienten steht. Und da ist der Herr Rupert Mehringer, der Papa an der Ecke. Das ist auch von uns vom Forschungsteam ein ganz, ganz großes Dank. Die Familie ist das A und O, sonst würde so eine Studie auch nicht möglich sein. Also vielen, vielen Dank, dass ihr das auch möglich macht. Jetzt Hirn-OP. Hirn-OP, hat dich das geängstigt?
Ja, natürlich. Also ich habe mittlerweile schon, also vor der letzten Operation, schon 55 Vollnarkose gehabt. Und dann habe ich mir überlegt, noch eine Operation, ob das überhaupt noch der Körper mitmacht. Und also deswegen hatte ich schon ziemliche Bedenken, aber es ist alles hervorragend gelaufen und der Körper hat es immer noch gut akzeptiert.
Super, genau. Das ist natürlich auch das lief super. Willst du uns jetzt beschreiben, wie der Forschungstag für dich aussieht, wenn du zu uns ins Labor kommst? Du wohnst nicht sehr nah bei München, muss man sagen. Du hast eine ordentliche Anreise, dein Tag ist ja voll. Und dann fährst du zu uns und was passiert dann so an so einem typischen Forschungstag bei dir?
Also so ein typischer Dienstag und Freitag ist also erst einmal einen Tag vorher freue ich mich schon sehr, dass ich am nächsten Tag wieder ins Labor nach München reisen kann und darf. In der Früh um 8:30 sowas wache ich auf. Dann werde ich natürlich gewaschen, angezogen und in den Rollstuhl transferiert. Und so gegen 10 Uhr kommt dann begrüßt mich der Transportservice. Immer recht freundlich, also das sind zwei, die ich schon lange kenne, also schon immer. Und wir begrüßen uns immer recht freundlich. Genau, und dann bin ich ungefähr 1 Stunde, 50 Minuten Autofahrt. Also ich wohne 1 Stunde von München entfernt, ungefähr. Und bin dazu gegen 11 Uhr im Labor.
Genau, und dann passiert ja was ganz Besonderes, ne? Wenn du im Labor bist. Was passiert denn da als erstes?
Also erst einmal werde ich immer auch im Labor herzlich begrüßt.
Genau.
Meine erste Aktion ist immer die Kaffeemaschine und erst einmal einen Kaffee trinken. Erst einmal quasi ankommen. Also ich muss sagen, das ganze Team ist unheimlich nett und freundlich und hilfsbereit. Also ich fühle mich wohl.
Genau, dann schließen wir ja die Messfühler da oben an. Und was arbeitest du da so im Labor? Was sind im Moment deine Aufgaben mit dem Ingenieur und dem KI-Team zusammen?
Ja, momentan sind immer jedes Mal 4 verschiedene Objekte dran. Also zurzeit mache ich, die Übung heißt Center-Out-Bewegung. Also ich muss quasi einen Mauscursor von der Mitte nur mit Gedanken in ein vorgegebenes Ziel steuern.
Super, ne? Du hast 8 oder mehrere Orte ne, auf dem Computerschirm. Du stellst dir vor, der Cursor soll dahin und klappt das schon?
Sogar sehr gut und sehr schnell. Also natürlich in der Tagesverfassung gab es manchmal noch besser und noch schneller, aber ich habe immer eine sehr hohe Erfolgschance. Also 80-90% habe ich immer, erreiche ich immer.
Das heißt, du kannst den Computer jetzt schon steuern, oder? Mit deinen Gedanken, mit dem Cursor? Was würdest du dir jetzt wünschen? Jetzt will man ja nicht nur den Computer da irgendwie ansteuern. Was sollen wir denn jetzt machen mit den Signalen als nächstes?
Also natürlich würde ich mir wünschen, wenn der Cursor funktioniert, ja, so Zusatzfunktionen, also quasi schon dass man durch bestimmte spezielle Tasten vom Keyboard auswählen könnte. Und natürlich ist das Ziel noch viel fortgeschrittener, einen Roboterarm steuern, nur mit Gedanken.
Genau, ne? Das heißt, wir haben jetzt schon die Cursor-Kontrolle auf dem Computer. Das heißt, der Computer folgt jetzt bald deinen Gedanken und jetzt kommt dann bald der Roboterarm. Wir werden nachher noch von den Ingenieuren hören, was da alles möglich ist. Wir müssen ein bisschen, glaube ich, auf die Zeit auch achten vielleicht, aber gibt es, wenn das erlaubt ist, aus dem Publikum eine Frage oder so? Gibt es jemand, der oder die gerne den Michi was fragen möchte, wie das so ist als BCI-Pionier? Machen wir nachher? Ja. Hast du noch etwas, was du mitteilen möchtest, als jemand, der eine Erfahrung macht, die in diesem Raum niemand hat und auch auf der ganzen Welt nur ganz, ganz wenige Menschen gemacht haben? Wie ist das für dich, in so einer Forschung dabei zu sein?
Also für mich ist das mittlerweile sehr stolz und ich bin froh, dass ich den Punkt, den ich Angst hatte, überwunden habe und ich hoffe, dass noch in Zukunft sehr viele Leute dazukommen, die auch einen Pioniergeist haben. Also mein Ziel ist es ja hauptsächlich in Zukunft viele Leute, die leider einen Querschnitt erleiden, wie auch immer, ihnen zu helfen und gleich am Anfang schon zumindest einen großen Fortschritt zu erleichtern.
Gut, wunderbar. Ich glaube, das ist ein Applaus wert. Vielen, vielen Dank. Ich bin auch ein bisschen nervös gewesen, dass du den Mut aufgebracht hast, hier uns nach oben zu kommen. Ich mache das auch nicht jeden Tag. Da hast du ganz toll gemacht. Michi ist noch ein bisschen da. Wenn Sie Fragen haben, gerne noch. Ja. Das Buch, genau. Du hast ein Buch geschrieben, ne?
Ja. Also bei mir selbstverständlich, weil ich denke, dass meine momentane Lebensgeschichte und meine Lebenssituation schon etwas Besonderes ist. Aber natürlich eine Autobiografie über mich, über meinen Lebensweg, über meine Geschichte verfasst.
Das Buch, genau, das heißt, wie heißt das Buch?
Seit dem Tag danach. Hallo, ich bin immer noch der Michi.
Genau. Gut, also überall, wo es gute Zeitschriften und Bücher gibt. Ja? Gut, vielen, vielen Dank. Wir geben jetzt weiter. Dankeschön.
Vielen Dank. Danke, Michi. Genau, es gibt, wollte ich gerade sagen, es gibt einige Exemplare hier, falls jemand reinschauen will. Wir haben gerade schon davon gesprochen, dass das Ziel ist, dass Michi den Roboterarm bewegen kann. Das ist die perfekte Überleitung. It's my pleasure and my honor to introduce one of our closest, or my closest partners, Lorenzo Masia, who is the director of the Munich Institute of Robotics and Machine Intelligence, one of the top institutions in this world. This is why we are privileged to have you, Lorenzo, who is also a friend. The stage is yours.
Thank you very much for the invitation. It's an honor for me to speak here. It's a bit challenging after this fantastic scientist that spoke before me. I'm just a humble engineer, and a mechanical engineer actually, even more humble. We're going to talk about what are the technology that comes after brain-machine interface. It's mainly robotics, and this is what I do for a living. So just a brief introduction, because I'm quite brand new in the Munich environment. I assumed duty around February 2025 as executive director of the Robotic Institute at TUM. And with me, there are other people working, Professor Lilienthal, Steinbach, Schillig, Rixen. We manage an institute that is almost more than 110 professors, converging PhD students more than 1,000, 200 senior scientists, several peaks of excellence, Leibniz Award, European Research Council, grantees, and 2 Humboldt professorship. And we graduated from 2011 more than 3,000 students in robotics. Our idea is forming the intelligentsia of this field, on this sector that is right now rising, also accompanied by AI, with an increasing trend that is dramatic. And we need to keep the pace of Asia and the United States that are right now winning the race. So it's a big, let's say, challenge for me and all the professors. When we speak about TUM is number 22 in the world for reputation, but if you go on computer science ranking, artificial intelligence ranking, and robo ranking, and you take the voice robotics and worldwide, TUM and our institute is number 1 in the world, and Germany should be proud of it. Of course, all this work has not been done by me, has been done by my colleague and my predecessor, Professor Hadarin. What I'm trying to do is consolidating what has been done and further expanding. Over the last year of my directorate, I expanded the research line. The first one is robotics and AI for security, defense, and aerospace. The second one is the RoboGym, that has been an investment from Neura Robotics, one of the champions in robotics. In the first year, we had investment up to 20 million between private and public sectors. So we are not going to consolidate, we are going to further expand, and we are going to stand number 1. Also because someone will want my head if this number changed to number 2. And of course, since I come from this environment, I try to boost also the direction in medical robotics, assistive technology, teaming up with the excellence persons that are here at TUM in brain-machine interface. So I will talk about exoskeleton. It's something that is quite known, more science fiction, but I have to tell you, it's a reality right now. There are several teams. My team is quite established. Who was the first inventing an exoskeleton was invented for industrial duty, and it was Ralph Mosher from 1967, General Electric. We're talking about 348 kilograms of machine that was defined like a symbiotic unit with the alacrity of man's information and control system coupled with the machine. So this control system coupling was completely missing. It never worked. However, this was the spark that ignited the big fire of assistive technology, rehabilitation, engineering, and human augmentation. We're going to talk about these things a bit. Right now, technology just scaled down in terms of, let's say, weight, and become by far much more controllable. And this is my field. We are not talking anymore about exoskeleton, but we're talking about exosuits. An exosuit is a device that can be worn like a cloth and has sensors and actuators completely on board. You have to imagine to have a parallel muscles that works with your muscles, an artificial parallel muscular system. It's extremely lightweight. It doesn't cost anything with respect to a big exoskeleton. This one for future commercialization, of course, is by far much better. And it's by far much more controllable. So how does it work, an exosuit? Well, basically, they work as amplifiers of movement. We detect the motion of a person. We amplify this motion just having motors that pull strings that are in parallel to your muscles. We test them extensively in industrial application, in medical application, in older adults, reaching the state-of-the-art of metabolic reduction consumption when you use this technology. And of course, we have to integrate this technology also with the brain-machine interface. And I'm here to tell you why. So I told you that they work as an amplifier of motion. So here, there's a lack of capacity of grasping a simple object because it's missing the strength. The neural system is not firing enough muscle fibers, but when you provide this kind of technology, the missing amount of force is replaced by the exosuit itself. Now the question is, how does these things understand when provide force or not? Well, there are several examples. The simplest is voice control. This is a spin-off from my previous group. You will hear this person that is affected by spinal cord injury and was not able to hold any object, just controlling the exosuit, saying Hanshu zu, volume up.
Hanshu zu.
You feel the actuation that lock the hand and the object in place. That residual capacity of motion is used to make an occupational task.
Hanshu zu.
Hero is the dog. So we are providing that missing capacity of movement, without which otherwise the person would not be able to do a simple action in everyday life. And we know exactly that this simple action changes completely the quality of life when these people are able to execute. Let me change. So here, spinal cord injury, very reduced amount of minimal capacity of motion, is wearing an exosuit and now is off the exosuit. But as soon as I turn off the exosuit, this residual capacity of motion is amplified into a motion that of course not is a functional motion. But yet, we succeed in providing assistance. When the motion, the residual motion is so low, there's no way that this person will be able to perform any functional task. Then we have to pass to a second step, that is the step of implantation. And you can do it implanting sensors and electrodes in the central nervous system as well as in the peripheral system. And here we are talking of electromyography. What is electromyography? Laser? No laser. It's the capacity of understanding how much electricity the contraction of muscle are generating and getting this electrical signal and feeding into actuation of the system to provide the missing force. You can do it with electrodes on the surface of the skin, or you can put needles. That is by far much more accurate, but of course is also much more invasive. We do these things with Imperial College, Professor Dario Farina, and we are able to detect a single muscle fiber activation and provide this signal that are extrapolated from the muscle activity directly into an exosuit. I'll show you an example now. So this person, if you see with the hand, is both hands impaired. But when we provide the exosuit and we extract the signal from the muscles, we provide additional capability and strength to grab an object and allow this person basically to drink or to feed himself. So this is an example of another, let's say, implant that is not a brain implant, but is a muscular implant. But of course, we have passed from detecting residual motion of not having motion and extrapolating signal within the body via invasive techniques. What is the next step? Well, the next step, of course, is when you are not able to also extract signal from the muscles, that is the worst case scenario, to extrapolate signal from the brain, like Professor Jacob previously explained. But the problem of extracting from the brain and then feeding an exosuit is that you have a system integration, or you should have a system integration capacity that is extremely complex. And usually it's not one person or one-man show. It's a multiple team show. And that's why what is my role as director of the Institute is the one of putting people together, handling the egos, and make them converge towards a single challenge and target. So the idea is teaming up, of course, with Bernhard Meyer, Simon Jacob, the team of Dr. Zavaglia, putting the two people at TUM that are expert in wearable technology, and funding a new professorship, thanks to Minister Blume, that is not here anymore, but from our heart, we actually, try to attract here the best talent that we can. And TUM is capable of attracting talent. I don't know if it happened for me, but for others, it happened, quite well. And then creating a continuous stream of capacity and skills in order to also affirm ourselves, not only in Europe, as Professor Meyer was saying, but in the world, as one of the strongest teams in brain-machine interface and assistive technology. Thank you very much.
Thank you very much, Lorenzo. Talking about world leaders, I'm very happy to introduce Rainer Birkenbach, the CEO of Brainlab, which has been partnered with me for over 30 years and now is endeavoring to do the same collaboration even closer with BCIs. And as I said, probably you noticed, we're completely dependent on the accuracy of the machines and the willingness to develop them, and therefore we can't do it with public funding. We need people from the industry and the medtech especially, and Brainlab is local, and that means we have another advantage over a lot of other people. I know.
Thank you very much, Bernhard, and welcome. Good morning also from my side. Lorenzo just said his background is mechanical engineering, so my background is electrical engineering, so we have it almost covered at all now entirely. And I almost forgot I'm presenting myself because I was so fascinated by the talks, and I looked around the audience, I could see that many of you also were like really fascinated by the topic. For me personally, this is also very special because it shows how modern technology and modern neurosurgery, what it can achieve in reality. And I also know where we come from, and we work together since decades, and the technology has advanced a lot. So when we started at Brainlab, what we did, our first product here on the left side, that actually was a planning software for neurosurgery, to plan complex neurosurgical cases, to make them safer, to make them accurate, or to enable those surgeries at all. And I just took a picture out of the very first printed brochure we had showcasing our very first, that was our product portfolio 35 years ago, that was the whole planning suite basically. The adoption of this technology back then was really slow for a couple of reasons. First of all, the back then neurosurgeons typically had never used a computer. Computers in the operating room didn't exist. But there were also a lot of technical difficulties. First one was compute power. The lack of compute power was basically everywhere. To load data, to visualize 3D graphics, even simple algorithms calculated for minutes, sometimes hours. And that problem obviously completely went away. When you look at your smartphones in your pockets or the smartwatches on your wrist, they all have way more compute power than what was available back then. The second one was actually getting the data into the machine. You might wonder what this big box on the left side is. This is a tape drive to load magnetic tapes, because back then in the hospital there was no network. So the images of patients were stored on those media types. And just look at those megabyte data down there and compare it with what Professor Jakob just mentioned on how much data is generated basically monthly today. So loading a patient data set, a CT scan or an MRI scan, that in itself was a task of an hour or longer. And the other problem was the accuracy of the image data itself. So on the left-hand side, you see an MRI scan from the early 1990s, and you can see the image thickness, how bad the resolution was. So the thickness of a single MRI slice was about 10 millimeters. And that was obviously the maximum accuracy you could get out of digital planning. So all those problems, obviously, are solved today. So technology had been advancing a lot, and this enabled us also to advance our product portfolio. And I will now show you how digital planning and the application of digital planning looks like today. But before I start, I would like to make this analogy. I think we're all using our phones, I think every day, to navigate, and we also use them to navigate even if we know our way around Munich, because we want to have the additional information. So the statistical layers like restaurants, public transportation, traffic jams, etc. And we also visualize our data very differently. There's maps, satellite images, and augmented street view either on your phone or directly built into your car. And we have built a technology that is very similar, but for the human body. So our maps are the images of the patients, CT images, MRI images. Our information layers is the information about the human anatomy, where functional areas are located in the human brain. We have a navigation system for the operating room, and we can visualize the data in multiple ways. And I will now take you through a neurosurgical workflow and show you how seamless integration really makes a difference. So we start in the office of the neurosurgeon, where the neurosurgeon is using our server-based software to first familiarize himself with the anatomy of the patient. We now take AI to extract the information out of those images, so we're building a sophisticated model, and we're now building a personalized digital twin of this patient. And in the next step, we will use an AI-powered tool to confirm the target of the surgery, in this case, the tumor. And we're using this information now to update the digital twin. You'll see this right now in the top left corner. Now it's updated. And in the next step, we will now map the so-called fiber tracts. The fiber tracts are the information highways or the telephone wires in the human brain, and areas we absolutely want to avoid during surgery. And here we're looking for the connection between the brainstem and the tissues surrounding the tumor. So this plan is now sent to the operating room, where the surgical team can look at an aggregate of the plan. So they can add and remove layers of the anatomy, like the layers of an onion, and they can start to simulate the craniotomy, which is the opening of the skull during surgery. And this plan is then sent to the Brainlab navigation station. That's where we capture the physical world, so we can now precisely track this instrument in the hand of the surgeon or any other surgical instrument, and we can now navigate the surgeon towards the target, in this case towards the tumor, and we can navigate the surgeon to bypass all the critical structures we have earlier identified. And in neurosurgery, the microscope is a quintessential tool, so we're precisely calibrating this to our navigation station, and now in return, we can inject the digital information, the plan information, the information out of the digital twin right into the view of the surgeon while he or she is resecting the tumor. And you can always take this plane, move it around, look beyond to see what critical structures are basically coming. And this is just one workflow. So we can take those building blocks from our technology, from software, data, services, and infrastructure, and apply them to multiple clinical challenges. I will now show you two planning examples related to the BCI context. The first one is a patient with epilepsy. So when you treat epilepsy surgically, you first need to know where the center of the epileptic seizure is, the hotspot basically. And one way of doing this is by implanting many electrodes. So between 10 and 15 electrodes are implanted into the brain, and then they measure the electrical activity. And you can imagine you need to precisely plan the location of every single electrode precisely, so it reaches its destination, but it also avoids critical structures like blood vessels, for example. And then we use navigation to implant every single electrode right to its target destination. So there's different patient, different view. You can see how many electrodes are going deep into the brain. The other example is, this is kind of a predecessor of modern BCIs, deep brain stimulation, short DBS. Here you implant electrodes deep inside the brain, and you apply an electric field to your target area. And if you do this precisely, you can apply this electrical field to the area to effectively stop the shaking, the tremor of, for example, Parkinson patients. And here you see how this looks like in the planning software. So the electrode has the individual electrical contacts visualized. So we plan precisely where each contact should be placed within the brain. We can simulate the electric field. So this is a finalized plan where you see the two electrodes at their target location. You can see the fiber tracts, and you can see the electric field. That's this yellow bubble. So you plan, you simulate, and then intraoperatively you use navigation to precisely position each electrode. And for all those complex cases, you can either visualize them on the screen, or much better for those complicated cases, you can visualize them in the mixed reality space. So the surgical team can use mixed reality glasses. You can enlarge the plan, the 3D brain, like really big. You can move around it, and you can brief and teach the whole surgical team prior to entering the operating room. And those complex cases, they really require optimization along the way. So every step really matters when it comes to the implantation of brain-computer interfaces, from planning to navigation to intraoperative imaging and beyond. And why is this so important? We want to achieve the highest safety, we want to achieve the highest accuracy, and we want to have very efficient workflows. So speed also matters. And every step matters. That's also true in a partnership. So we are very proud to be part of this journey together with Professor Meyer and the excellent clinical team, also with everybody from Technical University in Munich. And it makes us really proud that we're doing this all right here in Munich. Thank you very much.
Thank you very much. Now we go to something which is, of course, also related to what we do to patients and what it means if you have your thoughts available to everybody, basically. This has ethical implications which are very, very hard to grasp. And we're lucky to have a very, very prominent institute for ethics at the TUM. And Georg Starke will talk about the ethical implications because his specialty is neurotechnology, right? So, welcome.
Thank you very much, Professor Meyer. Thank you very much for having me. It's a pleasure being here. My name is Georg Starke. I'm a senior researcher here at TUM at the Chair for Ethics of AI and Neuroscience, the first of its kind in Germany. And it's a particular pleasure to not only complement this panel with a perspective from ethics, but also to continue after Michael Mehringer, because indeed one of the questions that has driven much of my research in the past years is precisely what does it feel like from a first-person perspective to use such neurotechnology, and even more specifically, what does it feel like to use AI-enabled neurotechnology? Are we moving towards what some hope, others fear, is a kind of hybridization with two mutually adaptive systems, the neural interface on the one hand side and the human brain on the other hand? And does it feel maybe, as one participant in our studies put it, feel like being an iPhone, but without worrying about it? And of course, we are not the first ones to think about these kinds of questions. The numbers of people using this technology is, as we have heard, very low. So most studies so far have only looked at one specific technology, one specific place where this has been investigated qualitatively. And of course, what we see is it's highly dependent on the technology. And not only on the technology being used, but also on the condition. And some things, for instance, are of course universally shared as positive experiences, improved quality of life, improved symptoms, increased daily activity. Others, such as the pre-surgical fear that we already heard about earlier, is universally seen as something challenging. But other things really depend on the context, right? So for instance, if we think about this frequent, at least in ethics and increasingly also outside of ethics, worry that maybe neurotechnology somehow impacts personality or human behavior, then it really depends. Are we tackling a motor symptom, then this may be a worrying unintended side effect, or are we talking about something where maybe this changed behavior, this changed personality is exactly what we are aiming for, so for instance in the context of obsessive-compulsive behavior. And now, of course, we were not happy to just look at research that others have done, but in fact what we did was conduct the largest multi-site study of experience of patients treated with AI-supported neurotechnology across Germany, Switzerland, Canada, and Italy, including also Professor Zucada, from whom you will hear later on. And we explored phenomenological and ethical questions in our research. Now, this is, of course, as you can imagine, a trove of findings with so many people being involved. So since we want to talk about invasive neurotechnology specifically here, implanted neurotechnology specifically, just to give you one flavor how this matters. So we talked to people with implanted devices on the one hand side, and they came up with very strong images for how they perceive this technology with view to their self, with relation to their self, drew parallels with tattoos they had, and said that accepting a stimulator, so this is from a patient with a deep brain stimulator, into their body was like accepting a foreign body inside them. or even more strongly, that their deep brain stimulator is theirs, it's inside me, it's part of me, and I don't want anyone touching it. It's like taking a hand and cutting it off if someone messed with it or wanted to forcefully explant it. And this contrasts quite heavily with other non-implanted devices, where the relation is much more hands-off with view to relation to self, where people see it more as a kind of another tool that's trying to help them from a medical point of view, and they don't see really this conflict, this merging of man and machine that we may see in the other instance, and commonly compared it to pharmaceutical drugs, right? Like just taking another pill. We also see this quantitatively if we compare implanted and non-implanted devices, where a much higher proportion of patients reported that they see the neurotechnology as part of themselves or very strongly as part of their body in comparison to non-implanted devices. Now, what does all of this have to do with ethics? If we assume that there's really this strong connection between sense of self, if people perceive a technology as part of their body, then this creates questions with view to what happens, for instance, if the company running a study, implanting a study loses funding, what happens then to the patient, and they really worry about it, who takes care of them. And it's precisely this kind of worry that has sparked a lot of regulatory debates also in the past few years. There's now many guidelines and reports internationally from the OECD. There have been recommendations on the responsible implementation of neurotechnology and how to translate this into practical policy from the Council of Europe, including one report on privacy and data protection in the context of neurotechnology and neural data that was just voted on this week, Tuesday and Wednesday in Strasbourg. There's been a report on human rights and neurotechnology, or late last year, the first truly global recommendations from the UNESCO on ethics of neurotechnology. Now, maybe also with many of you coming from industry, this may look like a familiar pattern where we are regulating something in a very nascent stage, and are we over-regulating this? And I think I would slightly push, being the ethicist here, back against this, because I do think that having something like a truly global guideline for ethics of neurotechnology is actually quite helpful, because we are operating, after all, within a kind of complex web of trust, not only between the physicians and the patients, but also between the companies, the oversight bodies, and these trust. This kind of trust forms webs, right? Where disrupting a single strand may impact the entire web. So having an ideally global regulatory space for this is quite helpful. And to conclude, I do think that to promote or ideally maintain and safeguard this kind of trust that we still see in very high levels in medicine, three items are key. We do need this kind of appropriate careful regulation and oversight without killing innovation. We also really, and that's why I think it was so beautiful that Mehringer was here on stage, have the voices of those most intimately affected by this technology heard, so patients or participants involved in the design, alongside clinicians, alongside the companies, potentially also alongside caregivers, ethicists, and others. And finally, we do need to not only get it right, but we also need to get it across. So we need to have clear and honest communication on what these really promising technologies can do, walking this fine line between hype and fear to avoid public perception that may be misleading and then put people off. And with this, I would thank you all for your attention. And yeah, thank you very much.
Since the topic is very important, we invited two speakers speaking about ethics. Caroline Green from Oxford gratefully came here. Thank you very much. The stage is yours.
Okay. Hi everybody. As you have got my very long name here. Actually, ich bin gebürtige Münchnerin und hieß mal Caroline Mosler. Das war einfacher. Back to English. I'm from the Institute for Ethics in AI at Oxford University, and it's a real pleasure to be here today to be speaking to you about this. So I see my role at the end of what has been such a mind-blowing session to actually go into some of the ethical issues that were dotted around and mentioned across all the various different talks that we heard. And I was really heartened to hear just how much more nuanced all of these talks were compared to maybe the more political talks, where it's all about let's build faster and better and everything is great. And I just want to stress, as an AI ethicist, we often hear, oh, what you are here to slow down everything, and it's all negative. That's not the case. Ethical development and AI development can happen at the same time. So just to go into some of the points that we've already heard, I'm going to jot them down and then give some color to them. I think the first that I want to raise is around participation and co-production in the rights of people with disabilities and people with chronic illnesses and conditions. So the case that we've heard here, obviously people who are extremely ethical, who are creating this technology in very safe spaces and in a very thoughtful way, and here alongside people with disabilities who are often really marginalized and things are done to them rather than alongside them. So what happens though once this technology becomes more widely available? And there are two pressing topics I think here that we should pick up on. So first of all, Simon Jakob, you mentioned just how many people there are in the world who could benefit from this technology. So the very basic question of equity and equality is who is going to have access to this technology and who's going to pay for it? And this is not just limited to this technology. Obviously, that's a health equity issue more generally, but I think it becomes really pressing when we can just see what is actually possible and what's available. And if you look into some parts of the world where people can't even access some of the most basic healthcare yet, how do we go about this? But I was heartened to hear that there's at least one professor here in Munich who thinks that in 15 years we will have solved all problems. So let's see, let's do that together. The second immediate question when it comes to people, rights of people with disabilities are something that I see in my work with people in care all the time. And they seem quite basic, but they're really important. They're around consenting, can they go back on their decisions? Do they know what they're doing? Specifically when it comes to such really sensitive data like brain data. And again, one of our colleagues mentioned that earlier. This is a whole different sphere that we need to think about. And what's really important, and that's why I love being here, is that we actually start these conversations with people in the room. Because what we've seen previously with generative AI, the new models, they were created in silos of experts, and then they were unleashed onto society, and now we can't really catch up with all the governance issues that we are seeing and the social issues. So it's not only a technological issue and the AI of the technology, it's more widely a social issue. So let's come together, let's start working on these topics together as and when these technologies become more widely available, that we have answers to them. I now want to go to another point that you, Professor Meyer, picked up on, human enhancement. So let's take the circle wider. Often, new kind of medicines and so on, they are created for a specific use case. And then there comes the pressure behind it, well, let's commercialize it. Let's make it more available to people, more widely. So what if, and you said that this is going to happen, this technology becomes more available for people who are healthy, who do not live with any conditions, but want to use it to enhance who they are. And there actually is an entire philosophical tradition called transhumanism that believes that we should use technology to enhance, to go over our human capacities and capabilities and who we are today, to improve who we are, to live longer, to become smarter, and so on. So there is this really big elephant in the room, is do we actually want that? It's a very big philosophical question. Where do we want to say, well, is this something that we in our societies want to see? And obviously we could say, well, we're already using other types of medicines, breast implantation, for example, even though you might look perfectly good, is it not for anybody to decide what they want to do and what they want to implant in themselves? But I think it's a really important question here of where do we want to go with humanity? What does it mean to be human? That's one of the essential questions that we hear in AI ethics. And what I'm personally concerned about is once there is a commercial pressure behind making this available, and in Silicon Valley we already see it quite a lot, is who actually benefits from it? Is it the tech companies? Is it the people who are implanting it or not? Again, there's also an equity issue. If we do then have smarter, better, more enhanced humans, whatever that means, who has actually got access to that? So some really, really big issues that we won't be able to answer today. But again, coming back to my first point, we need to have these conversations in the open. And we can't just say everything is great, let's just go ahead because we don't want to lose the race. It's something that we have to have as a society, because otherwise people are concerned, they are scared, and we will have narratives of doom and gloom, which are just not good for anyone. And the last point I want to pick up that was mentioned by you, Simon Jakob, I think too, was around brain data. So if you think about it, what we're going to have here is access to what is extremely sensitive and very private data. What do we still have at the moment? We're already being watched everywhere on the streets, on our phones, what we're doing, right? We often don't think about it, but actually we see in our work that that's something people are really concerned about. Also knowing that's how tech companies are being built, that's what they benefit from, is our data. So now you've still got your head. You can still think, I don't know what you're thinking. That's your private space, but this is going to become available, and maybe even your dreams, as we heard earlier too. So again, this has huge governance issues, and they're not completely new issues. We've already thought about this. We've started thinking about it through GDPR, privacy rights, and so on. But we now need to take these issues much further, and we need to think about new governance structures, neuro rights. What does that mean? And there are some proponents working in American universities who are already great advocates who are saying that we should have new human rights that are all about preserving our brain data and who we are. So I think there was a lot that we would all want to talk about, so that concludes me, and thank you very much for having me.
So thank you very much for giving this broad perspective, because I feel a little bit pressured, because what started as a thought 12 years ago and ended up to be a lucky shot and going viral, takes or puts some pressure on me what I'm doing, and therefore I'm very glad that you stressed my point, that this is the most decisive thing. If this is going to work, and it's quite sure it's going to work, it's going to change society. And that's beyond my reach, and there needs to be a discussion about this.